Hello, and welcome to the lecture for Chapter 2, Discovering the Universe for Yourself, from the Cosmic Perspective Fundamentals. I'm going to split this chapter into two lecture videos, one for the first two sections, and that's the one you're currently watching, and then one for the later sections. In all of the chapter, we're going to focus on observations of the night sky and how that helps us understand the movement of our home, Earth, the moon, and not just the movement of Earth relative to its own axis, but the movement of Earth around the sun. Okay, so full Earth movement, movement of the moon, and I suppose also how that relates to our observations of the planets in the solar system and stars. Okay, so there's a lot of 3D thinking here. There's a lot of imagining a ball in your room moving around. You have to look up and imagine this. You have to imagine a floating ball, that's the sun, a tilted ball, that's the earth, that ball going in a circle. Think about those consequences. Look at the pictures, the diagrams, and imagine them move. Okay? Okay. So, Section 1, 2.1, Patterns in the Night Sky. Our goals here are to talk about what does the universe look like from Earth, why do stars rise and set, and why do the constellations we see depend on latitude and time of year. Okay? So, very good questions there. All right, so with the naked eye, we can see more than 2,000 stars as well as the Milky Way. When we talk about as well as the Milky Way, you might say, hey, hold on, aren't the stars just part of the Milky Way? Yep. The Milky Way really is just a region of denser packed stars, okay, and more nebula. So we're seeing a lot of that interstellar gas as well. And that's when we look into the plane of our galaxy. Because if you think about it, our solar system is mostly planar. It's like a disk composed of a few tiny little specks of matter spinning around a much larger speck of matter, the sun. Okay, very, very spread out, dispersed, but disk-shaped. That disk is slightly tilted relative to the much larger, more fluid-like disk that is our galaxy. And when we observe the night sky, at some point, we're going to look into that relatively narrow band that is our galaxy. It only takes up a small angular section, more about angular observations of the night sky in just a moment. The Milky Way only takes up a small angular section of the sky because it is a disk, okay? If the galaxy was a cloud and we were in the middle of it, we'd look in all directions and see the effects, okay? We wouldn't have this band of different looking sky. Now, have you seen this firsthand? Well, maybe if you've been out in the desert, right? You know, if you look up, you let your eyes adjust to the darkness. Of course, in this photograph, this was taken with a longer exposure. So more light was allowed to pour in on some sort of sensor or film, and that allowed for a photo that looks different than the human eye would ever be able to discern it, even letting your eyes adjust. Okay? That's why it's so dramatic in this case, but it's always there, just needs the right tool to see. And by there, I mean this observation of the Milky Way. Okay? Right. So, constellations. Okay? So we split up the sky into constellations. Constellations are the same name that are given to the traditional constellations, this idea of philosophy and mythology all rolled up into the night sky that would have been easy to see for ancient peoples without city lights and street lamps. So that idea has continued over into the modern world, but we've refined it and we split up the sky into 88 constellations. And they're like puzzle pieces that leave no gaps and fill the entire sky in these sort of rectangular shapes. Within that rectangular shape might be a traditional constellation like Canis Minor, all right? Or Orion. But there's some that we've never heard of because there's 88 of them. And there's all the constellations in the southern hemisphere as well. You're never going to have to memorize all 88 in a class, okay? It's just there's familiar ones and unfamiliar ones, and they cover the entire sky, okay? That way when we talk about coordinates, we can say, oh, this star or this distant galaxy or this nebula is in this constellation. And then it applies to a map. We can also give its exact coordinates numerically. So the constellations are just an extra bit of information. Redundant, but helpful for the human mind. So the brightest stars in a constellation, what do we know about them? Think about this question. What makes the most sense to you? It's okay if your intuition's wrong, but have an answer. Okay? They definitely don't all belong to the same star cluster. So let's not misunderstand what a constellation is. It's just splitting up the sky, not splitting up space. All lie at about the same distance? No, definitely not. Okay? Because the sky is not the same as space. That's just a projection of all that light. It can come from anywhere. And they may actually be quite far away from each other. Of course. A constellation may be composed of relatively dim stars that are only a few light years away, and a couple really bright stars that are hundreds of light years away, all that appear the same brightness from our perspective on Earth. Right? So, case in point, the distances here would be much more dramatic. This is a shortening, but you could have some stars further away, some stars closer. They could be, at different angles relative to each other, but the light all gets essentially projected onto this imaginary thing, this is a new term, called the celestial sphere. Sounds pretty neat. Well, all it is the sky, okay? But unlike the idea of the local sky, when you stand in a flat field and you look up at the sky, it's all of the sky around Earth. Whereas the local sky is only half the sky around Earth, because you're limited by the horizon. You can't, if you're a person on the planet of the Earth, and I have another diagram that will show this quite clearly, but if you're a person on the surface of Earth, you can't see the sky on the other side of the planet because the planet's in the way. So my little stick figure would not be able to see Sculptor, this constellation right here. The planet would definitely be in the way. Okay? They would be able to see Aries and all the constellations that are above them. Okay? So, you see the little lines are back. These are the little rectangular puzzle pieces. These are the 88 constellations covering that sphere. Like if they all cracked apart, it'd be like an egg cracking into a bunch of little rectangular fragments. Okay? But a perfectly spherical egg. Now, the celestial sphere is going to be a projection of Earth, treating Earth like a perfect sphere. So if you get into the exact math of it, then yeah, maybe it's not a perfect sphere. But the reason I say it's a projection is because the celestial sphere has some characteristics that are just taken from Earth. It has a North Pole, it has a South Pole, and it has an equator. Now notice each of those is the celestial pole and the celestial south, celestial north pole, and celestial equator. But they're just continuations of the Earth's equator and pole. We just took that information from the Earth and extended it out. And the relative size of the celestial sphere is completely arbitrary. In this picture, it's showing what? A few dozen times bigger than the Earth in the middle. That's just for convenience. The celestial sphere could be about the same size as the Earth, because again, it's just an imaginary projection. But it makes it very helpful to have coordinates, because now in addition to referring to a star that's located in a particular constellation, just for quick reference, you could say, oh, I have a star, say this one here, and I know exactly where it is relative to the celestial equator, so I would have an angle relative to the celestial equator, or I could compare it to the celestial North Pole at a different angle, and then relative to my current location, I could have what's called a declination. I could say, okay, well, I'm standing here on what looks like Europe, if you look very closely at the world, right? See, I drew my little stick figure standing in Eastern Europe, since this is Africa here, right? South America. And if I think of the 3D nature, this star I drew, we'd have to come around to get to it this way, see? And that could be its declination. Or we could go the other way and have a right versus left declination. And I bring that up because that would be an exact coordinate of that star in your sky, okay? They tell you exactly where that star is located. Now, some of those things are going to depend on where you're located, okay, longitudinally, namely declination. Other aspects are going to depend on where you're located on Earth latitudinally, and that's going to be these angles here. I call this one 1 and 2 because they're different angles. Okay, and other aspects of where the object is, where the star is, depend on the time of night, your time, because the Earth spins. Thus, depending on the what sunlight you're being exposed to, the rise time and set time of that star that you can see, right, because you can't see it when the sun's up, are going to change. So you have the exact coordinates, but exact coordinates that are constantly changing because the surface is constantly moving relative to all these stars and the constellations with the stars in them. Always moving, okay? Because the stars are fixed. They move so slowly relative to us that they might as well not move at all, okay? And we'll talk about those slow movements. So the point is, though, that the Earth moves so fast relative to the stars, okay? All right? The celestial sphere. All right, and there's a lot we're going to come back to in this diagram. And the last thing is, what is this weird belt that doesn't sit right along the celestial equator, but instead is offset? What the heck is that? It has a weird name, an interesting name. It's called the ecliptic. So the ecliptic is the path of the sun through the celestial sphere. Okay? That's not a real thing, right? The sun isn't moving relative to us, but yet we talk about the path of the sun. That's kind of jarring, because that's the thing about the celestial sphere. The celestial sphere is not real. It's just a concept. And that concept has a sun that moves relative to it. Okay? Of course, in reality, from a bird's eye view, a cosmic bird's eye view, we're, of course, orbiting the sun. But why is it offset? What's that all about? That's the tilt. And that's going to be a big idea we come back to. And what tilt? The Earth's tilt. This angle right here is the Earth's axial tilt. We're going to come back to it because it's hard to understand at first pass. Okay? At least from my experience it has been. It's an idea I'm going to stress. And furthermore, the tilt is tied in beautifully with the seasons and understanding why we have seasons here on Earth. Okay? So we need all that. But here we have the first telltale sign. The ecliptic does not lie on the celestial equator. Okay, so the angle of that tilt, the ecliptic tilt relative to the celestial equator, is 23.5 degrees. Okay, that is exactly the Earth's axial tilt. Okay, here is the projection of the Earth's equator creating the celestial equator. Okay. The sun's apparent, remember, because the ecliptic is not real, the sun is not literally orbiting us. The sun's apparent annual path around the celestial sphere. The ecliptic is a path that takes one full Earth year to complete. So that means that, depending on the time of the year, we know where the sun is going to be in the celestial sphere, so we know what constellations the sun is going to be sitting on. Would we see that constellation? Well, no. Because that constellation is behind the sun. And you can't see stars at night unless you happen to be in the path of totality during a solar eclipse. Aha, okay? So hold on to that idea. That makes sense to you, okay? And then I already mentioned the poles, okay? So the ecliptic, the sun's apparent path through the celestial sphere. And that's useful because that's the way we see the sky. Okay, so you understand that, yeah, sure, we can just not talk about the celestial sphere and only talk about the sun's, or the Earth's orbit around the sun. But that's not what we actually see when we look up at the sky, is it? That's the point here. We need to make that step, that bridge in our understanding, to be able to look up at the sky and make sense of it. Because only then can you make sense of bigger ideas in astronomy. Okay, just summing up some more ideas I already mentioned. North celestial pole, south celestial pole, and the celestial equator. Okay, good summary slide here. Okay, we already talked about how the Milky Way is a band of light. It makes a separate circle around the celestial sphere. And let me recall Let's see if it actually shows up on either of them. Yeah, here it is. So you can see the Milky Way way up here, that band. And if we were to look at the back side of this image, if I could get this to rotate, that band would continue down around and kind of would bend down lower on the back side and get closer to the celestial equator. You can kind of see it's already tending in that direction. It's already kind of tending downwards. And as if we were to follow it around, that's what it would be. It would be, again, a circle around. And the reason that the band that is the Milky Way, that is the galaxy that we are part of, is not lined up with either the Earth's equator, thus the celestial equator, nor the ecliptic, is because everything is tilted relative to everything else. We're tilted relative to the plane of our solar system. The plane of our solar system is tilted relative to the plane of the galaxy. Okay? Visualize that. That's fun. Okay? There's so many opportunities for just thinking, sitting there, seeing in your mind's eye. Right? What a wonderful exercise. Okay? So here we are in the Milky Way. This is further explaining that idea of the galactic plane. In many directions that we can look, we are looking at a relatively clear view of the distant universe. There are still stars in those directions because we are not at, say, the very, very top of the galaxy, and there are so many stray little stars. There are even these things called globules, which are kind of little packets of stars that are essentially out of the plane, but there's very few of them. Okay, so they're out of the galactic plane. Sort of remnants, things are thrown off, right? It's not perfect. It's not just like a exact, it's certainly not a 2D shape with all the stars, right? But it's more planar than it is spherical. It's more disc-shaped. Spiral galaxy, it's called. So, but there are many directions we can look and we can see much fewer stars. But if we look into the plane, that's why it looks all dark, especially to a long exposure or adjusted eyes without city pollution from lights. Okay, light pollution. When we look in the direction, we see that. We see all that smudginess. We see those star nurseries. That's what all these big chunks of gas are, okay? These big blue sections, especially the blue spots, are where stars are being born. And we just see more stars, so it's denser packed. It's a brighter band of light, strewn across the sky. Right? And in fact, if you think about it, because of all the tilts, there's one hemisphere that is going to be looking more this way, and there's another hemisphere that's going to be looking more that way. Okay, we'll all see all of it, but there's going to be one hemisphere that is more tilted in that direction, and that's the southern hemisphere. That's the most spectacular views of the Milky Way are in the southern hemisphere. Imagine being out in the middle of the dark bush of Australia. You see a sight of the Milky Way that is incomparable to anything we'd see in the northern hemisphere. It just so happens. Okay? That's the idea. You can look into it, or you can look away from the galaxy. Right. So, remember that local sky idea? Let's get back to it. So the local sky. Now, if you can measure things in the local sky as well. Remember how I talked about those angles? Probably confusing on first pass, that idea of declination and latitude, celestial latitude, and how that could exactly tell you. It could be a very specific, very precise location of any object in the celestial sphere. Okay? Well, you can also talk about the exact location of any object in your night sky, because you also have fixed references. Okay? Your local night sky. You have a fixed reference that is your zenith, and you have a fixed reference that is your horizon. 0 degrees for the horizon, 90 degrees for the zenith. And then you can also talk about exact angles relative to north, west, south, and east. So you could talk about angles like this. Right? This one here would be 90 degrees. Okay? Relative from west to south. So, in the same way, you have a precise system for talking about the location of a star. But it's totally different, although exactly convertible, to the precise location in the celestial sphere. Okay? Now, those are pretty intense calculations, let alone understanding them, right? Or maybe it's understanding exactly this idea of precisely defining the location in the celestial sphere of a star and precisely defining the location of a star in the local sky. And then think about how you would actually go about doing that in terms of all those degrees and angles, okay? So it's too much for the course to actually ask me to do it, but I want to stress the idea that it's possible, okay? And that that's the process for astronomers. That's the process. If you have a telescope that is giving you coordinates, or a automatic system, like a computer operated telescope, those are the calculations that the computer's doing. Okay? So, back to the local sky. Let's make sure we at least understand the terms before we move on. Altitude is the angle above your horizon, and direction is the angle along the horizon. So the 90 degrees I drew between west and south would be direction. The altitude is the angle like this one here. That's an altitude angle, and then this would be a direction. And up here you can see the direction is southeast, because this particular star is exactly above, or it's actually not. It's kind of in the middle. There it is. But it's exactly halfway. So in fact, if it is exactly halfway, if it's truly southeast, and say not southeast or something, then this angle here would be 45, because it's halfway between 90. Okay? So that's great. But of course, those stars are going to be moving throughout the day, or the night, really. They're going to, because every star rises and sets. And if it doesn't rise and set, it's a circumpolar star, and there are plenty of those unless you're exactly on the equator. More on that in just a moment. But it still moves. It spins. Okay? Okay. New coordinate system. This one's probably actually easier to understand than the celestial sphere, because it's a half circle. Thinking about a sphere and the whole coordinates in a sphere, that's trickier. This is just a hemisphere. So you can just kind of do those 2D sweeps of your hand. Okay? So some other key terms, I already mentioned one of them, or two of them really. Meridian is the line that passes through the zenith, connecting north and south, not east and west. It's very specific. That's the meridian line. Just a helpful reference point of splitting the hemisphere that is your local sky into two half sections. The zenith is the point directly above you, an altitude of 90 degrees, and the horizon are all points that are 90 degrees away from the zenith. So it's the entire horizon. It is a circle. Precisely a circle. Now, your local sky can be obstructed by trees, obviously, hills, buildings. So it's very rare, really. You have to be in a perfectly flat area to have the whole hemisphere. You always have something less than that. Okay? But the ideas still hold. All right. Remember that idea of angular size? And when on those first pictures, I said, look, when I drew lines across the Milky Way, and I said, oh, look, it doesn't really take up that much of the sky because it's pretty disc-shaped. Our galaxy is not a big cloud, but instead of disk, a spiral disk. Well, we're going to continue on that idea of angular size. And we have a real nice way of grounding it, okay? So the first way to ground it is actually flip back real fast and think about the angle of altitude. Let's not worry about the angle of direction right now. Let's just worry about the angle of altitude. So going from south to zenith is 90 degrees. If I continue on from the zenith back down to north, I've gone another 90 for a total of 180. So if I follow the entire meridian, or any such arc across the sky, then that is a 180 degree sweep. Okay? So in other words, we could split the sky from horizon to horizon into 180 degrees. All right? So now we want to think about how big something is relative to that full 180. Well, if you look at the moon, it's half of a degree. Okay? What does that mean? That's the size of the moon. Well, that's not very useful, is it? Instead, what it means is if you took the moon and you set one on the horizon, and then you stacked moons, one on top of the other, how many would it take to go all the way along the meridian, to go from horizon to horizon, passing through the zenith? Think about the number. 360. Okay? Because each one is a half, So that means it takes 2 to make a degree, and then you have to make 180 of those degrees, so that's 360. It would take 360 moons to go across the sky. All right. And the sun is the same angular size. Of course, you wouldn't see it at night, right? But the sun is also half a degree. Same size, half a degree. Okay? So, Polaris, on the other hand, big constellation, is about 5 degrees from tip to tip. Okay? Southern Cross is about 6, so the big constellation. Okay? And then, if you want to quickly think about that, maybe the moon's out in the sky, maybe you just, want to relate it to something that's a bit more real, then you can do a rough estimate with the average length of the human arm. Now, people might have longer arms, that happens, but it's pretty rare, right? And the idea is your full stretched out hand held like this. So now you're looking relative, right? See how that's also an angle, okay? So when you look relative to your eye, your hand covers 20 degrees. So 5 Big Dippers. A finger is 1 degree, so 2 moons, okay? Any fingertip, you hold it, hold up your fingertip, and you'll see the moon covers half your fingertip. And you might be like, wait, no, that can't be right, because it's probably daytime right now. You're probably listening to this lecture, watching this lecture. You're like, no, that can't be right. Do it. Go. Check it out. Because when you look at the moon, you can zoom in sort of mentally and optically with your eyes, right? Blocking out some of your peripheral vision. Right? That's the nature. It's not like we have 180 degree vision, right? Yeah. What is it? What is the angle of human vision right there? So taking up a certain amount of your vision isn't the same as taking up a certain amount of the sky. So do it. Hold up your finger, and the moon only covers half of it. I know, smaller than you think. And 10 degrees for your fist. Okay? So let's do a quick summary of the numbers here. So full circle is 360 degrees. Now, again, we don't see 360 degrees of space. The only way you do that is if you got on a spaceship and you went out, far enough away from the Earth where the Earth isn't taking up most of your field of view. And even on the space station, the Earth takes up most of the field of view of the space station because they're not very far from the surface. But if you went off in distant space, then you could get a 360 degree view. Okay, but the idea still holds. The idea of taking degrees and splitting them up. Because a lot of things, unlike the moon, which is a half degree, are going to be tiny fractions of a degree. What if we talk about the angular size of just one star, right? What if we talk about the angular size of Mars or Jupiter, Saturn, Venus, okay? Well, when we do that, we need smaller degrees, smaller divisions of degrees. Or another one would be the angular size between stars. That's a very important one, okay? Or even the angular size of star wobble or star movement relative to us. Okay? Well, anyway, we can split one degree into 60 arc minutes, and we can split 1 arc minute, notice the change in notation from degree to a little minute notation, into 60 arc seconds, just like time. But this isn't time. This is angular divisions. And here's the idea. 1 degree getting split into 60 arc minutes, and then every arc minute, it can be split into 60 arc seconds. So then, how many arc seconds are in 1 degree? Got an answer? 3,600. Okay, so there are 3,600 arc seconds in every degree. That means there's a lot of arc seconds from horizon to horizon passing through the zenith, aren't there? Okay. So, what's the meaning of this? Well, we can relate this whole idea of angular size, remember, to holding out your arm, and that's assuming your arm is a particular average length, because it turns out that there's a formula, there's geometry here, not just degrees, and the geometry tells us that the distance, the actual physical distance, can be related to the angular size, and thus allow us to find, if that's what we're interested in, the physical size. That often is what we don't know, because we're stuck here on the surface of Earth in our breathable atmosphere, protected by our magnetic field, and we look up into space and we see things, we don't know how big they are. All we can do is measure their angular size, but then if we know their distance, and there's ways we can find that, then we can calculate their physical size. And we'll talk about how you would find distance. Okay? There's a few crucial ways, including Kepler's third law. Okay? So that's pretty cool. Allows you to find physical size. And here's the formula. Basically just comes from the wedge of a circle. Comes from a bit of geometry of a circle, taking a little slice. Okay? 2 pi to 360. That would be converting from degrees to radians, is that 362 pi business, if you wonder where the 2 pi comes from. If you remember seeing radians at all in a math class. Okay? But the important thing is you need this formula. You don't need to know exactly where it comes from. But it allows you to either calculate angular size if you know physical size, the way it's kind of written here, or I can multiply by the reciprocal of 360 over 2 pi, which would then just be 2 pi over 360, and that would give me physical size. I'll write this out for you. So then physical size would just be angular size multiplied by 2 pi over 360. Okay? All right. So why do stars rise and set? I've hinted at this a lot. I've said it a few times, but a picture is worth a lot of words, isn't it? It's because the Earth rotates about its own axis. That is the only reason that stars rise and set. It has nothing to do with their movement relative to us. It only has to do with our rotation around our own axis. Okay? Because we're spinning about our own rotational axis, which happens to be exactly the same by design as the North Celestial Pole. Okay? And that makes the appearance of stars that come up in the east and then take a path across the sky and then set, or don't set at all, but instead spin in the circle. Okay? Earth rotates from west to east, so stars appear to circle from east to west. Get it? Okay? Again, visualize that. Imagine a little stick figure. We'll draw them kind of near the North Pole, easier to think about. And they're looking up, right? They're looking this way. What do they see? Okay? And when you look at this, where's the North Celestial Pole in this picture? Where's the North Celestial Pole? So right there. North Celestial Pole. How do I know that? Because that's the only point that wouldn't be moving. That's a fixed point in the sky. There happens to be a star really close to it in the northern hemisphere, Polaris. There are no stars particularly close, no bright stars particularly close to the South Celestial Pole. Okay, so there's not that same guiding star. There's ones that turn in pretty tight circles, but none that really stay fixed over the entire night. All right? And if you look at that, then the altitude of the North Celestial Pole, as indicated by the only fixed point in the sky, is your latitude. They're equal to each other. Okay? How do I know that? Well, because we can overlay the information of the local sky on the celestial sphere, onto the celestial sphere. So what we have here is in this lighter blue, this would represent someone's local sky. Okay? This whole thing. With direction and altitude and a zenith, and there's our someone, see the little person here? Doop, 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 doop. Okay, that little guy, little gal. So there's their zenith, okay? Here's the celestial equator. Here's their horizon. They're not equal to each other, right? Some stars never set, right? Here's a circumpolar star. It comes down close to the horizon, but it doesn't set. It just keeps going. There could be other concentric circles up here that never set. All right? So, I told you what that is. It's the North Celestial Pole. Okay? Why do the constellations we see depend on latitude and time of year? They depend on latitude because your position on Earth determines which constellations remain below the horizon. Because your position on Earth determines which stars are circumpolar, and those stars form constellations. They depend on time of year because Earth's orbit changes the apparent location of the sun among the stars. Okay? The ecliptic. We're getting back to the ecliptic. All right? So latitude and longitude They're terms that show up in the celestial sphere. They're, of course, terms on the surface of Earth itself, right? Over here in North America, we have a longitude of, some 130 degrees west and about 38 degrees north, okay, in Northern California specifically. Right? So position east or west, and it's relative to some arbitrary line called the Greenwich line. Due to the imperialism of England, it became the choice, and we just decided to stay with it for now, right? There it is. That's considered a longitude of 0 because there's no natural choice of longitude. The circle just keeps going, right? The poles make sense because the rotation is relative to them. That's where our axis of rotation passes through. So as I said before, if you're at the North Pole, then your zenith exactly matches up with the North Celestial Pole. If you're somewhere else, then your latitude can be determined by the location of the pole relative to the horizon. The location of the pole relative to the horizon will always give your latitude. In this case, in the southern hemisphere, we measure the location of the pole relative to the horizon and the location of the south celestial pole, 34 degrees. You can make that measurement, and that would exactly tell you where you're standing, how, right, on the actual surface of Earth, right, in this case, like in southern Africa, how low below the actual Earth's equator you are. It is a navigating tool. It's a location tool, okay? One that has been around as long as people have understood the sky. For thousands of years, humans have been making calculations like that. Yeah, you might think of the European Dark Ages. The idea of the Earth being round was taboo, but that hasn't always been the case. Certainly, ancient Egyptians understood that the Earth was spherical. Okay? So the altitude of the celestial pole is exactly equal to your latitude. That's a good one. Just like, okay, remember that, and then remember how to find it out, how to look at the image if you kind of get stuck in being able to visualize it. But definitely remember that that's the case, always. Okay? The North Star Polaris is 50 degrees above your horizon, due north. Where are you? Answer this. Pause it if you need to. You're at a latitude of 50 degrees north. Okay? Back to the ecliptic. The sky varies as Earth orbits the sun. As the Earth orbits the sun appears to move eastward along the ecliptic. Right? Remember, it takes a full year to cover that band that doesn't exactly lay on top of the celestial sphere because the Earth's tilt. Okay? At midnight, the stars in our meridian are opposite the sun in the sky. Okay? So at midnight in August, the star that is above us is Aquarius. The constellations and the stars in Aquarius. At noon, the star that's directly overhead is Leo. But you can't see Leo because what else is directly overhead at noon on August 21st? The sun. Okay? Maybe not directly overhead unless you're at the equator, but it's overhead. And can you see constellations at noon? Of course not. But August, if you're familiar with the zodiac, is associated with Leo. So it's the constellations you can't see that correspond to the zodiac for that month, because those are the constellations that are being blessed by the sun. They have the honor of being with the sun, riding along with it, right? If you think ancient mythology, okay? So quick summary here. We can see over 2,000 stars in the Milky Way with our naked eye. The position on the sky belongs to one of 88 constellations. We can specify the position of an object in the local sky by its altitude and its direction along the horizon. We can also specify the coordinates of a star in the celestial sphere. Okay? I just added that, so good note you can consider. Why do stars rise and set? Because of Earth's rotation. Why do the constellations we see depend on latitude and time of year? Because of your location, because of your latitude, and because of where they are in the celestial sphere. We can't see southern constellations unless we go to the southern hemisphere of our planet. But also because of the time of year, because the sun makes some invisible during certain times of the year, because they rise and set with the sun. Okay? And again, of course, rise and set is just because of the Earth's rotation. All right, so that's a great summary, and we're going to move right on to section 2. Okay, and let's continue right on with section 2.2, the reasons for the seasons. This is what I hinted at before. This is a return to axial tilt and its consequences in full form. Okay, so what causes the seasons and how does the orientation of Earth's axis change with time? Those are separate questions. Okay, we'll spend most of the time on the first question. What causes the seasons? True or false? The Earth is closer to the sun in the summer and further from the sun in the winter. What do you think? Okay, I told you axial tilt is the reason, but are we still closer in the summer? Think about it. Yep, hint. When it is summer in America, it's winter in Australia. So there can't be a right answer here. Because literally, if we're closer in our summer, we'd have to be further in their summer. And summer is summer, right? Yeah. False. Okay. Can't be the case. Seasons are opposite in the north and south hemispheres. So distance literally cannot be the reason. Okay? Otherwise, our definition of summer and winter would have to be changed. The real reason for seasons involve Earth's axial tilt, the 24.5 degrees that our rotation axis is tilted relative to our orbital axis, or relative to the plane of our orbit. All right, so here's the idea. Look at Earth, right? See that little tilt? Just like the way globes are made? That's the axial tilt. All right? You can see it as Earth goes around the sun. And notice the way the tilt works. It's not like the tilt is always away from the sun. Here, in December, okay, the tilt in the northern hemisphere is facing away from the sun. In June, the tilt is towards the sun. That just has to do with the way that rotation works, the way that angular momentum works. The tilt has to be preserved, which means its relative angle towards the sun changes. Towards in December, or way in December, towards in June, okay? Which makes December winter in the northern hemisphere and June summer in the northern hemisphere. Because when we're tilted towards the sun, it's summer, and we're tilted away from the sun, it's winter. Okay? Make sense? For the northern hemisphere. Because think what's happening here. Look at the light, right? Look at the way the light is distributed. There's more light up north in June. See that? And it's not like literally we're a little bit closer, right? That effect is completely insignificant. It's the fact that there's longer days and more direct light. Especially longer days. Look at the kind of the path here. Imagine that path and compare it to the much shorter path down there. There's a longer path. Let me zoom in on that. Okay? See? See, this is the kind of the right where the sun touches the earth. And if you were on a point down here, you would take a shorter path to go from sunrise to sunset. Up north, you would take a much longer path to go from sunrise to sunset. Longer days, more direct sunlight in June in the northern hemisphere. And the opposite, of course, in the southern hemisphere. And what about the equinoxes? Well, that's where the axial tilt is totally misaligned with the orbit, and the whole planet is getting the same amount of sun. Exactly 12 hours of sun on both the September equinox and the March equinox, the spring and vernal equinox. Okay? There's some visualization, a lot going on in that figure. Because of that axial tilt, because of the fact that the ecliptic, the apparent motion of the sun through the sky over an entire year, are not aligned, because the ecliptic is not aligned with the celestial equator, we have the location of the sun changing over the season. Okay? So this variation is due to axial tilt. Okay? So the variation along that axis from axial tilt. Okay? This variation, which is much smaller in degrees, is due to the elliptical orbit. And we'll talk more about ellipses. It's the fact that our orbit is not a perfect circle, which we'll address actually in just a couple slides. We'll talk about in some more depth in a later chapter. And this is from elliptical orbit. Okay, not nearly as significant, and actually not significant at all for the seasons, just significant in that it is perceptible in the sun's location if you were to track it like this. Take a photo, every couple days of the exact same location, and then overlay all the photos, because that's what we're looking at here. Right? Some nice desert location here, at least, right? Desert garden, probably a university. Looks like this thing was built specifically to show the angle of the ecliptic. All right, at that particular latitude, of course. Okay, moving on. So Earth's axis points in the same direction to Polaris all year round, okay? And that, of course, would be the top of the axis, or the northern pole, right? Now, the south end of the axis points towards, some faint star that doesn't have a special day. So its orientation relative to the sun changes as the Earth orbits the sun. I showed that by drawing that red line in the 2 slides ago, right? So that the orientation towards the stars is unchanging, thus the orientation towards the sun is changing. Get that? Okay. Summer occurs in your hemisphere when sunlight hits it more directly. Winter occurs when the sunlight is less direct. And by direct, let's imagine our sphere here. Here's our axis. Here's sunlight. Okay. So where is it more direct? Well, in this case, the direct part is down here. And the indirect part would be, say, like up here. Because that sunlight comes in, imagine there's an atmosphere, there is, of course, around the planet. Sunlight, like this arrow, the topmost one, the uppermost arrow, has to pass through thicker atmosphere. And when it hits the ground, every single bit of energy of the sun is spread out over a bigger area. Whereas when it hits it directly, every little bit of sun, same amount of energy, spread out over a much smaller area. That energy per area has a very big effect. So we have 2 effects happening. Energy per area and length of the day, so total amount of absorbed energy. Okay? Now, those effects compound to make winter much warmer than summer. If there was no axial tilt at all, there still would be more indirect light at the poles, because it would still be coming in, same logic of passing through more atmosphere, because it has to pass through a thicker bit of atmosphere, as opposed to this, right? Which line is longer? This is the shorter line for direct light. This is the longer line for indirect light, right? So longer line here. Okay, more spread out. That would still apply without axial tilt. So the poles would always be colder. But big important thing is the poles would never be in complete darkness for months of the year. Because as it is, the poles are in a location where they get no light at all for a significant portion of the year. Of course, then they have many days where the sun never sets, but the sunlight's always indirect, and when there's none at all, it gets really cold, okay? So the fact that we have axial tilt makes poles that would already be cold much colder. So why doesn't the distance matter, right? Because I said the distance is perceptible as far as the shape of tracking the sun's location at a fixed location on Earth, but why doesn't it really affect the amount of heat we get? Well, the variation in the sun's distance is small, about 3%. So right away that should be like, oh, well, 3% variation, that's not a very big deal, Just common sense tells you that. The small variation is overwhelmed by the effects of axial tilt. So much so that there's no data to suggest that on average, summers in the northern hemisphere are hotter than summers in the southern hemisphere. And the reason we would suspect summers to be hotter in the northern hemisphere is when the northern hemisphere is tilted towards the sun, right, in June, that corresponds to about the point of closest approach to the sun. That's when we're 3% closer to the sun. So if there was an effect, then on average, northern summers should be hotter than southern summers. And this is south of the equator. Well, they're not. They just effects of seasons and the big currents in the air and just the overall effect of the energy coming from the sun. No, there's no average there. There's no data to suggest that our distance from the sun actually affects the seasons. All right? And the difference is, by the way, 15.2 million miles when we're furthest from the sun, and 14.7 miles when we're closest. Okay? 147.1, excuse me, and 152.1. Misread that. Okay? But and you can always think of and that variation, obviously not big. The number you always want to remember of how far we are from the sun is it's about 150. You can always take that as your average. About 150 million kilometers, which is a nice even number to remember. The Earth is 150 million kilometers from the sun. Okay? This is just summing up the special points, the same figure again, the equinoxes and the solstices. These are the special points. Okay? And the summer solstice is the summer in the northern hemisphere, but it's the winter in the north in the it's so excuse me. So the summer solstice is the summer in the northern hemisphere, but it's the winter in the southern hemisphere. So you can really call it the June solstice because that's a more accurate name that would apply to the whole Earth, right? So we can recognize solstices and equinoxes by the sun's path across the sky. How so? Well, the solstice is the highest path, the rise and set at the most extreme north of due east. Okay? So this right here has to be the solstice path. So you might wonder, like, okay, if that's the solstice path and the sun gets as high in the sky as it's going to get, why doesn't it get all the way up? Why doesn't it pass through the zenith? Well, it will only pass through the zenith if you're at the equator. So sun only passes through zenith at equator. Because at any other point, the highest point of the sun is dictated exactly by that axial tilt. Okay? So as you move away from the equator, the highest point that gets lower and lower and lower, okay? Until it gets to the point where if you're at the pole, if you're at the North Pole or the South Pole, the highest the sun ever gets is only the axial tilt angle. It's only 24.5 degrees. That's the highest the sun ever gets, okay? Whereas at the equator, the lowest the sun ever gets is 24.5. That's why the equators are so much hotter, okay? Let alone the fact that there are, as I said before, significant chunks of the year where there's no sun at either of the poles, right? Opposite times of the year, but both of them have the same length of time, okay? There's a symmetry there, all right? So the lowest path, rise and set, is at the December solstice, and then at the equinox is exactly it rises and sets exactly due west. Okay, so one thing that the whole world has in common on the equinoxes, and this is again just kind of just bringing home all these ideas, is that everywhere on Earth the sun rises due west and sets due east, only on the equinox. Okay, and only at the equator will it rise due west, take a path exactly like this, and set due east. Everywhere else, it will take some curved path, like the one shown in this picture. Okay, this could be in North America. Take some curved path like this, but still set due east. Okay. At the North Pole, on the equinox, it would rise due west as well, take a path, max out at 24.5, and then come back down. So take a real shallow path. Okay. So kind of similar to the one shown here, similar to the one shown here in terms of the December solstice path, except of course it's rising due west instead of rising so close to the south. So the path of the sun tells you exactly about the seasons. And there's so much there. There's so much about certain areas that get sun only certain times of the year. Maybe you've noticed that. All right? It's so important for, growing crops and all these considerations. So here we are at not the North Pole, but the Arctic Circle. And what latitude is the Arctic Circle? Well, I can tell you. The latitude of the Arctic Circle is 90 minus 24.5 degrees, which is, I'm just going to calculate this rather than do it in my head. It is, so 90 minus 24.5 is 65.5. Okay, so 65.5 degrees north is the latitude of the Arctic Circle. The Antarctic Circle would be 65.5 degrees south of the equator. How do I know that? Well, because I know that the Arctic Circle is the point where you have one day of the year where the sun never sets. You also have one day of the year where the sun never rises. As you go further north of the Arctic Circle, you get progressively more days of complete darkness and more days of midnight sun never setting. So the reason that I say then that information tells me that it must be 65.5 is I know I have to imagine a point where the planet's tilted just enough so that sun laying on top of the planet, being shined on the planet, can just touch that point that lies on the Arctic Circle. And here we have a day, that one day where the sun never sets in the Arctic Circle. Right? See, it gets right down to the horizon, but it doesn't quite set, and then it comes right back up. Right? And these are snapshots showing the duration of the day. Pretty cool, huh? All right? So, last thing we care about for the axial tilt is that it changes. Okay? Now, it doesn't change in its value. It's always 24.5 degrees, but it changes where it points. So right now, our rotational axis is pointing towards Polaris, a star that is many light years away. Okay? But since the stars aren't moving in any appreciable way relative to us over any, span of time that we care about right now, okay? Certainly not Earth years, right? That Polaris stays fixed and the axis is currently pointing towards it. But over a time span of 26,000 years, okay, so let's think about, okay, good chunk of time, that the Earth will make a full precession in its movement. So what's a precession? Well, the precession is just like a spinning top. You've all seen tops spin, okay? So as a top spins, it spins quickly about its axis of rotation, but more slowly about its precession axis. It precesses. Every spinning object precesses, as long as there's any initial misalignment between its axis rotation and basically a force axis or an acceleration axis, of which there is, okay? And that means that the Earth is precessing, okay, because of the forces of gravity from the sun. There's a precession in the Earth, okay? And in that 26,000 years, it's going to go from pointing from Polaris, or in 15,000 years, it will go from currently pointing from Polaris to the North Star being Vega. We'll have a new North Star, okay, in 15,000 years. 2,000 years ago, more like 2,500 years ago, when the constellations were getting their names that we use, okay, especially the Greek constellations that we use in science, that they weren't quite where they're located, right? 2,000 years is a significant amount of time. That's not, a half precession or a quarter precession, but it's enough that all the stars have moved since then. And all the star maps from ancient astronomers, ancient Greek astronomers, are no longer accurate because there has been that movement. And it's not because the stars have moved, okay? Now, the stars are moving, right? We talked, in fact, about how in 250 million years, the Earth makes an entire orbit around the galaxy. In that time, the stars themselves are pushing and pulling on each other like a little fluid kind of swirling around. But all of that movement is on the scale of millions of years. So any star movement is going to be on a whole other time scale. So effectively, a precession happens, a full 26,000 year precession happens with no appreciable star movement. Okay, it's the difference between tens of thousands of years and hundreds of millions of years, or at least tens of millions of years, right? Okay. But this idea of precession definitely affects the constellations, all right? So, summary here and end of this video. The tilt of the Earth's axis causes sunlight to hit different parts of the Earth more directly during the summer and less directly during the winter. All right, also changes the length of the day. We can specify the position of an object in the local sky by its altitude above the horizon and its direction along the horizon. Okay, that's just reiterating something we saw in section 2.1 as well. The summer and winter solstices are when the northern hemisphere gets its most and least direct sunlight, respectively, and the spring and fall equinoxes are when both hemispheres get equally direct sunlight. I always think of the equinoxes as neat events because that's when the whole Earth is experiencing the same thing. Okay, they're all getting 12 hours of sunlight. Of course, we know that the sun isn't taking the same path everywhere on the Earth, but it is taking the same time everywhere. Okay, and the tilt remains at about 23.5 degrees. Okay, so the seasons aren't affected. That's a good point. But the Earth has a 26,000 year precession, so the location of the stars in the sky, okay, does change. Whichever ones are circumpolar might not be, and the North Star changes. So all the relative location of the stars in the sky changes over time, over thousands of years. Okay, all right. So that summarizes all of section 2.2, and will be the conclusion of this video. Please check out the second video for this chapter. I'll continue on with section 2.3. Thank you so much for watching.